Hello and welcome to part 4 of the sketching functions series. In this video, we're going to be focusing on the last two steps in order to successfully sketch a function. We're going to take some examples and explain how to go through each one. The fifth and sixth step basically says that we need to find the first derivative to find all the critical points, and by critical points we mean stationary points, okay, or points where the slope or gradient is 0, and will determine the intervals where f of x is increasing or decreasing. Increasing interval means the interval where our function is having a positive slope or positive gradient, okay. Decreasing is the other way around, is the parts where the function is having a negative slope. So increasing, where the function looks like this or have a slope like this or like this or like this or whatever. Decreasing is when the function is having a slope like this, over this, or here. These are all negative slopes. These are all positive slopes. The difference between those is just how steep it is, how high the magnitude of the slope is. This is the steepest one. This is the most unsteep one, basically, if that's a word. Okay, the second thing is finding the second derivatives, okay, and determining where the intervals of f of x is concave up and concave down, and if there are any inflection points. Concave up is where the function looks like this, that's concave up. Concave down is when the function is looking like this. These are called concave up, okay, and this is concave down. So if f double dash of x is positive, then we have a concave up interval. If f double dash of x is negative, then we have a concave down segment or interval. An inflection point is basically a point where concavity change. Like, let's say we have this shape of the function over here, okay. Can you see that this first part, well, I will highlight in green, has a concavity that is positive. It's like it's tending to have this shape, right, which is similar to this shape, so it's a concave up part. However, the next part, like after this green point, the concavity tends to have a shape that's like this, right, which is a negative concavity. So this point where after or before this point concavity changes is called an inflection point. So an inflection point is basically a point where concavity of the graph changes. Here it changed from up, concave up, into concave down, so this point is basically an inflection point. Okay, so let's start by taking some examples. Let's say we have a function f of x equals 3x plus 5 over 8 plus 4x. So straight away, this is a rational function, so I need to take care of horizontal asymptotes, vertical asymptotes, and so on. And in these two parts go hand to hand with the vertical asymptotes part, okay. So for this video, we're going to be using 2 or maybe 3 steps, determining the vertical asymptote and then those 2 steps. So it's also very important to determine the vertical asymptote first, or where the function is undefined, basically, to be more general. So this function is going to be undefined if the denominator is 0. So let's find what value of x will make the denominator 0. So 8 plus 4x equals 0. Moving the 8 to the other side, and then dividing by 4, x is going to equal to -2. This is going to cause my function to be undefined, and in the video where I explained how to differentiate between a vertical asymptote and a hole, we can know that this is going to be a vertical asymptote, as we do not have any shared factor up and down. If we had an x plus 2 over here and and this I can simplify to 4 into basically x plus 2. So I will cancel this with this. Since there is a factor shared in the numerator and they're cancelled, then this x minus 2 is no longer going to be a vertical asymptote, it's going to be a whole, and so on. If you would like to check in details how to differentiate, click on the top right hand corner. It's super useful. So up until now we know that we have x minus 2 as a vertical asymptote. Okay, let's see part 5. What does it say? It says find the first derivative to find all the stationary points. Okay, let's do that. So f dash of x is going to equal, I know when I have a fraction or a rational function, how to differentiate it. It goes like this. Is the differentiation, let's say this is g of x, and let's say this is h of x. Okay, it's going to be the differentiation of the first function times the second, the denominator function normally, the minus the other way around now, the differentiation of the lower function into the first function normally, and everything over the denominator function to the power of 2. So this is going to equal differentiation of the first function, differentiation of 3x plus 5. And by the way, I did the whole series on differentiation. Click on the top right hand corner to view. So the differentiation of 3x plus 5 is going to be basically 3 into h of x, which is 8 plus 4x, the minus h dash of x. So the differentiation of 8 plus 4x is basically 4 into g of x, which is 3x plus 5, everything over h of x squared, so 8 plus 4x squared. So let's simplify a little bit. This is going to be 3 times 8 is 24, plus 3 times 4x is 12x, minus 4 times 3x is 12, negative 12x, and then minus 20 over 8 plus 4x squared. So I can see here that 12x and 12x cancels. 24 minus 20 is basically 4 over 8 plus 4x squared. So now this is my first derivative over here. So I can just copy it and move it this side. So this is my first derivative. Let's equate it to 0 to see if we will have any parts where the first derivative is going to equal 0. So I can see that I can multiply 8 plus 4x squared both sides, so I'll have 4 equals 0. This is obviously undefined, so this means that we will not have any value of x that will make our first derivative 0, so no stationary points. Stationary points are points where the gradient is 0, like this one over here. The gradient over here is going to be 0 because the tangent is horizontal, so this is a stationary point. However, over here in our function we do not have any stationary points. Okay, so the only critical point that we have in this function is x equals minus 2. So we need to test the behavior of the graph before this point and after this point. So let's try and do that. So we want to test, okay, our critical point was x equals minus 2. Okay, we want to test a point in the interval between negative infinity up to negative 2, anywhere between this interval, and then the second interval, which will be any point after negative 2, so negative 2 up to infinity. These are our two intervals, and we need to test the point. So let's pick any testing point over here. So any point on this interval, let's say negative 3. This is a point on this interval. And over here, let's say that x equals negative 3. This is our testing point. Okay, so this is the test point. And this over here is going to be f dash of x. We want to know the sign of f dash of x. And after that, we will determine if it's increasing or decreasing. So When I substitute x equals minus 3 into my f dash of x, I will get 4 over 8 plus 4 times negative 3 all squared, which is basically going to be a positive answer. Let's check. Yes, it's positive 1 over 4. So basically, it's positive. And since it's positive, is my function increasing or decreasing on this interval? Yes, it's increasing. Since I have no stationary points are points where the function goes from increasing, let's say, to decreasing. So it changes sign of the slope. So over here, since I don't have any stationary points, I will expect that the graph is always going to be either always increasing or always decreasing. Let's test that. So let's take a point on the second interval. Let's say a point between -2 and infinity is a simple point as x equals 0. So over here, I will test. So 4 over 8 plus 0, so 4 over 8 squared. This is going to obviously give me a positive answer. So the function is increasing. The function is always increasing, and this is what we determined over here. Okay. So now we have determined that where the intervals where the function is increasing and decreasing, and we said we do not have any critical points. So this part is done over here. Let's now look at the second part, which is finding the second derivative and determining the intervals where f of x is concave up and concave down, and if we have any inflection points. So let's see how we can do that. The first step is to find f double dash of x. So we will take this, which is this, and differentiate it one more time. So let's differentiate this over here. So f double dash of x, again, is going to be a quotient derivative. So we will use the same equation over here. So what is 4, or the differentiation of 4 is basically 0. So it's going to be 0 multiply h of x, which is 8 plus 4x all squared. So 0 times anything is basically 0. And then we have a minus. So minus the differentiation of h of x, the differentiation of this function. So what's the differentiation of this function? Using the product rule, I know it's going to be this power times the coefficient. So 2 into 8 plus 4x, and then reduce the power by 1. So from 2 minus 1, that is basically 1, or I can just leave it like this. And then I will multiply by the derivative of what's inside. So the derivative of 8 plus 4x is basically 4. And then I'll divide by the denominator function squared. So I will divide by 8 plus 4x squared all squared. So this is going to give me -2 times 4 is basically -8. So this is going to be -8. Oh, I didn't multiply. Yes, because in our quotient derivative formula, we have the differentiation of h of x, which is 2 into 8 plus 4x times what differentiation of inside times 4 times g of x, which is 4. So I have another 4 and I need to multiply over here. So I'll have -2 times 4 is -8. -8 times 4 is basically minus 32. So it's minus 32. Then 8 plus 4x over 8 plus 4x power of 2 to the power of 2 is basically everything to the power of 4. So this over here, I can cancel 1 with these 4 in the bottom. So I'll have a minus 32 over 8 plus 4x to the power of 3. And this is my answer to the second derivative. Again, let's see if there is any critical points in the second derivative. So if I equated the second derivative into 0, again, 8 plus 4x times 0 is 0, so I'll have a -32 equals 0. This is undefined, so I don't have any critical points in f double dash of x. And these critical points could be inflection points, because when second derivative equals 0, then we could have a potential inflection point. However, over here we don't. So let's move on. So let's again do a similar table like the one above. We'll take the intervals from negative infinity to -2 because this is the only critical point we have. And we will take the interval from -2 up to infinity. Okay, let's say that we have the test point. Okay, again, let's take the same test points, x equals -3 and x equals 0. And over here, we will evaluate f double dash of x to see its sign. And then over here, we'll determine if it's concave up or down. And we can erase this bit over here. Okay, so substituting x equals -3 into here is going to give me -32 over 8 plus 4 into -3. So 8 plus -12, that is a minus. And then minus power 3 is minus. And then minus divide minus is plus. So I expect a positive answer over here. And indeed, yes, I got a positive half. You guys try to do the same and see if you get the same answers as me. So we have a positive over here, which is going to be a concave up part of the function. And when I substitute 0 over here, I'm going to have -32 over basically 8 plus 0, which is 8. So 8 power 3 is positive. So I have a negative over a positive. So I'll have a negative answer. So this part of the function is concave down. So let's see how we can use these values to aid us in sketching, because this is our main aim. So what we said is that the function is increasing always. We have a vertical asymptote at x equals -2. So let's check. This is the function over here. Let's say x equals -2. We have a vertical asymptote, and I can see that the function is always increasing. So this interval, I can see that I have a positive slope where my mouse is. And this interval as well, I have a positive slope. Nowhere in this function where I have a negative slope. And again, I can see that the interval before -2, so everything to the left of the black vertical line is going to be a concave up shape. And I can see that over here. And anything after -2 is going to be a concave down shape. And I can see that over here. So this confirms our solutions, and this is how to aid you in sketching. So when you have these answers, first you start with your vertical and horizontal asymptotes, and then you start to see, okay, this interval I'll have a concave up, so it will give you an idea of the shape and so on. And this exactly what we will be doing in the next video, where we will combine literally everything we've learned throughout this series to sketch full functions, and I will show you how to do them. So let's take another example. So let's say we have the function f of x equals x squared over 1 minus x squared. So first thing, let's start by evaluating the x's that will make our function undefined. So basically anything that will make the denominator 0. So let's say 1 minus x squared equals 0. So 1 equals x squared. Square rooting both sides, I will get x equals plus or minus 1. So x equals 1 and x equals -1 are both going to be critical points, or points where my function is undefined. What are the natures of these points? Again, these points, I can see that they will be vertical asymptotes. Vertical asymptotes. I do not have anything to cancel with on the numerator to make them wholes. Okay, so I have two vertical asymptotes over here. Let's keep that in mind. Let's now do part 5. Let's try to find f dash of x. So f dash of x, again, this is a fraction or a rational function, and I will need to get the differentiation of it. So I'll use the same rule I used before. So it's going to be differentiation of the top function, so 2x times the bottom function, so 1 minus x squared, minus differentiation of the lower function, which is going to be differentiation of 1 is 0, differentiation of minus x squared is minus 2x, and then into the top function, which is x squared. Everything over 1 minus x squared to the power of 2. So simplifying, this is going to be 2x times 1 is 2x, then minus 2x cubed, and then I have a positive 2x times x cubed, which is plus 2x cubed over 1 minus x squared to the power of 2. I can see that this and this will basically cancel, and my answer will be 2x over 1 minus x squared. So the second thing is to determine the stationary point. So I will equate this first derivative to 0. So I can see that I have 2x equals 0. So x equals 0 is a stationary point over here. Okay, so to determine the nature of the stationary point, is it a maximum, is it a minimum, we will do the same thing, finding the intervals where they're increasing and decreasing, and this will help us determine if this point is a maximum or a minimum. So let's take intervals where we are considering all our stationary points. So x equals 1 is all our critical points. So x equals 1, x equals minus 1. This is a stationary point. This is a vertical asymptote. This is a vertical asymptote. So let's start by doing our table over here. So our first interval is going to be from negative infinity up to minus 1. Our second interval is going to be from minus 1 up to 0. Third one is going to be from 0 up to 1. Fourth one is going to be from 1 up to infinity. Because now we're considering all these points. So I'm considering basically this interval, the one before, the one after 0. Oh, no. Okay. So basically I'm considering every interval between them. Okay. And the intervals after and before the lowest and the highest one. Okay. So let's do a neat, nice table to help us visualize everything. So this first part is going to be the test point, and this is going to be f dash of x, and then we will determine if it's increasing or decreasing based on that. So let's take any test point over here. Let's say x equals minus 2 and let's define f dash of x. So where is f dash of x? Yes, it's this one over here. So 2 times minus 2 over 1 minus 2 squared power 2. I'm basically changing this x and this x over here into minus 2 and minus 2. So this is going to give me a negative answer over here, which means that this part is decreasing. Let's take another point between minus 1 and 0. Let's say minus 0.5. So over here, instead of minus 2, I'm going to test minus 0.5. And this is minus 0.5 squared. So putting that in the calculator is going to give me a negative answer. So this part is also decreasing, and I expect to have a change over here because 0 is a critical point. So the interval before 0, I'm going to have a value of f or a sign of f dash of x, and the interval after 0, I'm expecting to have a different value. So let's check. Let's take 0.5 over here. So this is going to be 0.5, and this is also positive 0.5. So I'm going to have 2 into 0.5 over 1 minus 0.5 squared all to the power of 2. This is indeed going to give me a positive answer, which means that the function is increasing over here. So I can see that when x was 0, the function went from decreasing to increasing. So the function was decreasing, having a negative slope, and then it started to increase after my critical point. That means that my critical point is a local minimum. So over here, our stationary point is a minimum. Okay, and then since there is no critical point here, I expect this also to be positive or increasing. So if we try to check any point over here, let's say x equals 2, this is x equals. So over here, I'm gonna change this with a 2. So this is going to be 2 times 2 over 1 minus 2 squared all to the power of 2. And indeed, this is also a positive answer. So this part is increasing. So this is our table that will help us later on when we're sketching the function. Now let's go and do the next step over here, which is step 6, finding f double dash of x. So let's change this back to x, and let's try to find f double dash of x. So f double dash of x is going to equal differentiation of this expression over here. So I'm going to differentiate the numerator first, which is going to give me 2 into the denominator, which is 1 minus x squared all squared. And then I'm going to subtract differentiation of the denominator, which is going to be power times coefficient. So it's 2 times 1, which is 2, into 1 minus x squared. And then I will reduce the power by 1. And then multiply the differentiation of what's inside. Differentiation of what's inside is basically minus 2x. And then I will multiply by the numerator function, which is 2x. Everything over 1 minus x squared all to the power of 2. So over here, what I can do is, I can say that I can take 1 minus x squared, okay, as common from these two terms. So if I take 1 minus x squared out, I'm gonna be left with a 2 from this term, and then minus, I'll be left with only 2 times minus 2x times 2x from this term over here, and then everything over 1 minus x squared power 2. And I can see that this will cancel with this, so I will just have okay, over here I'm not only left with a 2, I'm left with a 2 times 1 minus x squared. So 2 into 1 minus x squared. So this is going to equal 2 times 1 minus x squared. Let's actually do that. So 2 times 1 is 2 minus 2x squared. And then minus 2, this is going to be plus plus. So it's the same as 2 times 2x is basically 4x. 4x times 2x is plus 8x squared over 1 minus x squared. And this over here, the denominator is 1 minus x squared to the power of 2. So when I do the quotient rule, I should also power a 2 over here. So this is going to be power 4. And when I cancel 1, it's going to be to the power of 3. So simplifying this is going to be 2 minus 2x squared plus 8x is basically 2 minus plus 6x squared over 1 minus x squared power 3. So this is our second derivative over here. If we equate it to 0, which is basically meaning equating the numerator to 0, I can see that this is a positive answer. This, whatever x is always going to be a positive answer. They're added to each other, so it will never become a 0. So no inflection point, because no part where the f double dash of x is going to equal 0. So now what we will do is that we can copy our nice table over here and do it for f double dash of x. So if we can erase these bits and change this. Okay, we're gonna use the same test points. We're gonna use the same intervals because these are our critical points. We did not have any additional critical points from equating the second derivative to 0, so we're gonna use the same exact points. So over here, what I will do is I will take this and let's move it down so it's nice and in front of us. So yeah, so we will test when x is minus 2 over here. So it's gonna be 2 plus 6 times minus 2 squared over 1 minus minus 2 squared all to the power of 3. And we will check that this is going to give us a minus sign, and this is going to determine if it's concave up or concave down, because when the second derivative is minus, it's concave down. When the second derivative is positive, it's concave up. So this is down. The next part is when x is negative 0.5. So doing that on the calculator, this is going to give me a positive part over here. So this is a concave up part of the function. And over here, when x is positive 0.5, this is going to be also a positive answer, which is concave up. And when x is 2, I'll substitute x as 2 into the second derivative, is going to give me a negative answer, and you can check and double check with me on your own. So this is going to be concave down. So I can see that my function is going to be concave down from this interval. Anything before negative 2 is concave down. From negative 2 up to 0.5 is going to be concave up. And then anything after, from anything below negative 1 is going to be concave down. This is our interval. Between negative 1 and up to 1 is going to be concave up. And anything greater than 1 is going to be concave down. And let's test that with our graphing function over here. So first of all, we said that we have two vertical asymptotes, x equals minus 1 and x equals 1. Yeah, so as we can see, these are correct. Let's check our answers for the first derivative. First, we said that we will have a stationary point at x equals 0 and it's a minimum. And we can see that over here, yes, it's a stationary point and it's a minimum. We can see that in the interval before minus 1, the function is decreasing. And I can see that any interval before the black line to the left of the black line, I will have a negative slope. And then after, between minus 1 and 0, so between the black line and 0, I will also have a negative slope, and I can see that this part is also having a negative slope. And then from 0 to 1, I see that I have a positive slope, or the function is increasing. It's increasing. And then from 1 up to infinity, my slope is also positive since my function is increasing. So this is all correct and everything is working out. Let's do the same for the second derivative. We said that before minus 1, the function is concave down. We can see that this green part to the left of the black vertical line is a concave down. Over here, I can see that between the black line and 0, so from negative 1 up to 0, I can see that it's concave up. Yes, it's having a shape like this. And then between 0 and 1, it's also a concave up part, which is this part over here. And then after positive 1, so after positive 1, it's having a concave down shape, and this is shown on the graph as well. So everything is basically showing what we expected. So this is how you can use this information in order to plot your graph. So this is going to help you. First, you divide your graph into the intervals you have, okay? You plot your minimum points, you plot your x-intercepts, you plot your y-intercepts, and then you start to shape your point. I know that I will have, let's say, a vertical or a horizontal asymptote over here. Is my function going to look like this or like this? What will determine the concavity, right? If the concavity is down, then my function should be like this. If the concavity is up, then the function will have a shape like this. So this is how we use the information, okay, over here to determine the shape and sketch our function successfully. This is going to be shown thoroughly in the next few videos. I hope this video was helpful. Thank you very much for watching. Please don't forget to like, subscribe, and keep your notifications on to not miss the crucial next parts. And yeah, leave a comment. Thank you very much. Have a good day.